doing the Rife Resonator. I change the name on it all the time though. But yeah, so without further ado, let's jump right in. So yeah, I'm an electrical engineer in the biomedical option. I really like all kinds of engineering, but kind of wish I did more computer science kind of stuff though. Dream job would be with alternative electrical energy generation and transmission, but not a lot of companies really looking for people to do R&D in that. So my problem statement and is that I get some data here. So some of the data I found, I don't think I put a source in here, but I'm sure you can find it. Tattoo removal, it's very expensive. It's like 10 times more, at least sometimes, to get it removed than the initial cost to get it in the first place. So, like one session alone could cost anywhere from $200 to $500, and you usually have to get multiple sessions to get it completely removed with resonant laser therapy. And that could total anywhere from $1,000 to $10,000 for something that only costs $300 to get in the first place. I want to try to explore and see if there are better options available. So, what my project should do is it should be able to generate high voltages very cheaply and efficiently. And I need to be able to target and disassociate the tattoo ink molecules without harming nearby tissue. And it's based off of a design originally used for bacteria. So my design philosophy and strategy is that I'm trying to make this design so that it's cheap. For one, this is a bit of a pet project of mine that I've been working on for 3 or 4 years now. So I want to be able to keep the project, so I'm trying to make it as cheaply as possible. The design, it has to be modular, so I can put it through a wide variety of testing situations. And yeah, summary of project phases. So we did the capstone project in multiple phases. The first and second weeks we focused on the define phase, where we would find a problem or opportunity, and we would create a project, like a rough draft for it, to be able to solve the problem. By week 5, we started going to the measurement phase, where we would ask potential customers what they would like in the device that we wish to build, and engineer a design based off of the feedback and specifications that the customers provide. And by week 8, we get into the analyze phase, where we create multiple designs that meet the customer's specifications, and we pick the one that we choose to elaborate upon. And then by week 13, I believe it was, we develop a working prototype. And then after that, we just troubleshoot it, try to get it to work. So, project timeline, did pretty good up until weeks 8 through 13. I had trouble troubleshooting my design. So, the budget, I mean, most of my stuff, in terms of power supplies and equipment that I get through YSU, stuff like heat sinks and like wooden frames and spare wire, I just find junk in places. So my total expenses so far is a whopping $35 actually. So, customers and feedback. The only customers that I was able to get hold of was professors at the YSU biology department. And specifically what they wanted were things that were out of scope for me, like trying to integrate the power supply, the waveform generator, the microscope, the network analyzer to be able to identify the frequencies of the absorption frequencies of the samples that could be used. So, but the one thing that I did try to make my design around was how they asked to be able to target specific parts of the body, and I tried to create a design around that, as well as when I'm trying to measure how effective my design is, the only way you could really do it is to be able to use the design use the project while you're using a microscope to be able to observe firsthand what actually happens, whether or not it works. So you can closely monitor the reaction of a sample to know whether or not you're actually having any effect on it. So the basic procedure is as follows. So I need to be able to generate a high voltage at a wide range of pulsing frequencies. I need to be able to acquire a sample and somehow photograph it under a microscope to make comparisons. I need to scan a portion of the sample using a network analyzer to be able to identify the absorption frequencies that I would then later use my project to be able to send out pulses from my high voltage transformer at that specific rate. I would place the portion of the sample that I found the absorption frequency for, and I would put it onto the plates, which are the secondary transformer terminals, and I would then, under a microscope, while the device is turned on, I would check the sample for 30 seconds to a minute to note any sort of reactions. And if there are no reactions, then I would have to increase the output voltage. And if there is still no, or if there is a reaction, then I would also have to make sure that the reaction isn't due specifically to the voltage and not necessarily the frequency. So I would have to acquire another portion of the original sample, and I would have to try it at a different frequency at the same voltage to see if whether or not the frequency had any effect on the reaction with the sample. So for generating the high voltage, usually a turns ratio type transformer is utilized. A typical high voltage Tesla coil setup usually uses a capacitor with a spark gap setup. So I decided with my design that I could probably have a lot more flexibility for the frequencies that I could pump out of my coil if I use semiconductors, and because of that I ran into a lot of problems later on. But another feature that my device uses is that it transforms the voltage using what I like to call transient magnification, or the voltage through the induction coil formula, which is the inductance times the change in current divided by change of time. So essentially what I need to do to get this to work is that the output voltage is determined by how large of a change in current I have from 0 to whatever its maximum value is over the shortest interval of time. So, and idea for this kind of comes from an idea in mechanical engineering, hydraulics, I guess, known as a water hammer phenomenon, which is when you close a water valve really fast. Since water is an incompressible fluid, the water will carry its inertia and slam into the closed valve, and the force can be, there will be a momentary spike in pressure that will be enough to actually cause the pipes to contort. So you actually have to, in pretty much all piping, you have to have some sort of pressure arrestor to be able to give some place for that, for the water to expand up in, to be able to alleviate some of the force. So I wanted to see whether or not this could happen in an electrical sense. So here's some early schematics of my design. So basically in the second diagram, I'm trying to utilize a primary coil with very high capacitance to create current spikes. And I'm trying to utilize a secondary with high series inductance. The significance of using inductance in the secondary coil is that as how do I explain this? I forgot to incorporate a picture about this, but as you pulse or as you have current through an induction coil will increase proportional to the duration of the applied signal. So if you don't allow the current to promulgate for a prolonged amount of time, the current will never actually reach its maximum value. Therefore, it chokes the current into a brief voltage spike, I guess. I don't really know how to explain it well. But my design incorporates the use of current chokes to be able to safely make sure that within the secondary side, when I'm applying this to living flesh, that I don't end up accidentally electrocuting whatever I'm experimenting with. So I think that to be important. The design I'm using is based off of Nikola Tesla's 1898 lecture series, designed specifically for human experimentation. I pretty much followed the design almost exactly, except that I'm using semiconductors instead of capacitor and spark gap arrangement. Some of the advantages of it are that it's very cheap to build and it can withstand a variety of testing conditions, and I can also change a lot more of the parameters of the setup a lot more freely than I could with condensed turns ratio type design. And that the secondary coil also has very low resistance, which is good for quality factor. But the problem with this specific type of device is that it only works at one specific frequency that you have to tune the primary and secondaries to. So one way I overcome this is to be able to encode the frequency, the resonant frequency of the sample onto the resonant frequency of the coil using a quad Schmidt trigger. But the design roadblocks that I'm running into with this type of design is that I get a filtering effect through the primary due to the capacitance of the primary coil, which is in the nanofarad range. I don't know why I wasn't expecting this, so to fix this I would probably have to either find a way to isolate the gate of the MOSFETs I'm using so that they aren't affected by the current in the through the drain and I don't know how to describe it, but as a result of the filtering effect, I cannot generate large enough changes in current over small intervals of time. So, solutions. The solution that I'm currently using is just to refer. Found the TV the other day, so I just kind of took the high voltage transformer out of it, and I'm kind of using that. So, but I'm probably going to end up having to switch over to a variable capacitor and spark gap type arrangement, which is, you don't have a lot of flexibility with the frequencies that you can tune it to. There are some other things I can do to increase the amount of voltage. Interesting enough, there is actually a relationship between temperature and the amount of output voltage you can get. It's the one thing I got out of thermodynamics, I guess, was calculating that. So moving on with actually being able to apply the high voltage to be able to disassociate bacteria or other molecules is based off of the idea of how you can shatter glass with sound. Glass is a rigid object, and the molecular structure of glass is such that it has a very narrow bandwidth of frequencies that it will respond to, whereas the resonant frequency of the glass is determined by the shape. So if you try to pass a transverse wave that it resonates at the same frequency of the glass will not absorb it, but rather the radiation would pass right through it. But for some reason, if you use a longitudinal wave like sound, it more readily gets absorbed by the glass, and you can pump energy into it. So I'm trying to use the longitudinal-like nature of an electric field, which can actually generate audible sound. If anyone ever seen those videos with like a singing Tesla coil? All right, so we got a couple of. No, I mean I probably should have got a video of it, but you can actually, with the proper configuration, actually use high voltage to actually create sound waves. So, so with destroying bacteria, there's actually a lot of data out there that shows, for instance, with ultrasonics, that you can disable certain types of bacteria endospores using 70 to 200,000 cycles per second sound waves, and you can actually within 30 seconds completely disable the endospores, which I think is pretty cool. But bacteria has certain qualities that makes it different from glass, in that bacteria is elastic and not rigid like glass, and that it probably has a bandwidth that is a lot larger for which specific frequencies it would respond to. But I just think of it like a swing set, I guess, where even though the boundary of the cell wall can stretch out, it would behave like a spring and pendulum type system, I guess. So you want to be able to pump energy into the pendulum system when it's at the maximum points, because if you try to pump energy into the system when it's like halfway, the internal oscillations of the standing waves within the bacteria would interfere with the energy you're putting in, and you just create waste energy. So the timing is important to be able to stress the cell wall to the point where you can actually physically stress it using the input energy from the high voltage to be able to cause it to disassociate or for the cell wall to burst. And in case you don't believe me, I can show you a video. This is not mine. I have no idea how I would go about getting anything out from this, because I don't know how to put my video camera up to the computer. So this is happening, but it's gonna take a lot of hours. All right, that's what I get from embedded video. All right, basically you can see from a picture that the researcher in the video will broadcast a signal about like 10 kilohertz, and you'll see these cells will wiggle, and then it'll just stop moving and then burst like this one. So I pretty much spoiled the whole video for you. When it comes to tattoo ink destruction, though, tattoo ink is a lot bigger of a molecule and is often composed of heavy metal pigments, like any one of these actually is what it's like. There's actually lead in some pigments, which is I guess cheaper than alternatives, which is why they use it. I'm not sure that's still legal, but because the tattoo ink goes deep into the skin, current like laser removal methods has to penetrate deep into the skin, and lasers are not really good at penetrating deep into the skin. So what my system would do I would be able to create standing waves within the body that would how do I explain this now? If I were to, like, from here send a mechanical oscillation that would, I don't know, resonate that like, I don't know, cup over there, I could still send, like if I got the right signal, I could actually send a mechanical oscillation through the ground as long as it's connected to the same medium as a glass over on the table. I don't have any data of that, but I mean that's kind of the premise behind, for example, Nikola Tesla's earthquake machine, which is actually where he got a lot of the ideas for this. When I'm going to test this, I would have to be able to what have I talked about yet? To be able to assert whether or not the device operates as claimed, I would have to, under a microscope, be able to watch the molecules have to disassociate under the specified frequency, or I would have to take photographs, before and after to be able to compare. And there's kind of a bit of a problem in that a lot of bacteria you have to kill before you can view it properly. So usually what you have to do when you want to view a bacteria is that you have to kill it and then heat fix it and then stain it with dyes. And I need to be able to view it while it's alive. So I would have to come up with some sort of light filter. I would have to shine like certain wavelengths of light that would be transmitted and absorbed differently than visible light when you're viewing bacteria under a microscope. Already talked about that. External issues. So there might actually be some problems when it comes to trying to electrify a living tissue with extraneous amounts of electrical pressure. There are actually certain FDA guidelines for devices like this. And apparently, since the tattoo pigments are a lot of times composed of heavy metals, that can be broken down and more readily absorbed into the capillaries within the lower dermis and collagen matrix of the skin. these can be toxic when absorbed into the bloodstream, and it's not good. So next steps is I got a lot of them, so basically I gotta go finish growing my culture of bacteria and test that with my other samples. So yeah. But I've learned it's not fun doing a capstone by yourself. It's a lot of stuff to do. Time management, you heard that from literally everybody else. A lot of things that I didn't see coming that I feel like I probably would have a better job foreseeing, I guess, now that I've worked on an actual project to know how to identify potential roadblocks in the future. Yeah. Any questions? All right, Chad.
I'm not familiar with tattoo removal. I don't have any tattoos, but how is this different from conventional methods?
Oh yeah, I probably read mention it. So conventional methods, what they do is they shine certain wavelengths of laser light onto the area of the skin, which causes the skin to burn essentially and scar up, and it gets pretty scabby and messy. And it's actually effective with darker pigments, but with like lighter pigments, it's not very effective. And like if it's like a really large surface area, or if it's got a lot of detail into it, it's not very effective for removal. But if it's like something simple that doesn't have a lot of detail into it, then lasers can be used. It's still expensive, but it does work. Chaz again.
Follow-up question. So is resonating using your design operating advantage?
Yeah, so with my design, you can actually electrocute yourself, and it doesn't actually electrocute you because, as I understand from Tesla, what he says is that since the frequency is so high and the current is kept minimal using chokes and the voltage is high, what actually happens is that the charge is stored statically. That is, it's not actually moving anywhere. So what actually happens is that the air molecules around your body will actually be attracted to your body and absorb some of the charge and be carried off. And so you'll actually have this sort of inductive heating effect, actually. Instead of being, shocked, you actually like heats your body up. So, and it makes a lot of ozone, which is poisonous. But yeah, it's a lot safer than electric current at lower frequencies. So, you in the back.
You said you've been working on this for like 4 years, you said?
Parts of it.
So how did you come up with like the idea behind it? Like what led to that?
Oh yeah, I never talked about that, did I? So there was this guy in like the 1940s that supposedly was, he invented this microscope using different, so normally with like a bright field microscope, you usually just use like an incandescent light bulb to be able to view bacteria under a magnified lens. But the problem is with that is that the wavelengths of light that come out of the incandescent light bulb can, they could possibly all get absorbed or reflected differently than if you had different wavelengths. So what he experimented with was using red and blue and green light, and he found that he could see different bacteria that you couldn't see with a normal incandescent light bulb. And this led him to be able to identify and target certain types of bacteria, supposedly, that he believed were responsible for certain diseases. So he came up with a device that would be able to specifically target it in the 1940s using high voltage at whatever crude switching devices they had back then. And yeah, he got thrown in jail.
We need to take one more question. did you end up looking at well?
I started on it, and I don't know, couldn't garner any interest. I think everybody already had like an idea of what to do for the capstone, so I just kind of kept chugging along, I guess.
Because it's a really interesting topic. I would have thought you would have more takers.
Yeah, I really probably could have needed help. It would have been really easy to just join someone else's group and I don't know, actually like accomplish something, but I was stubborn.
I don't think he discussed his idea with others, right? He did not talk about your ideas to the other teams. Did you?
I mean, I don't know. I don't think I could get anybody interested in being able to electrocute people with stuff for some reason. I'm probably gonna keep working on this after I graduate.
Okay.